Hello, everyone. My name is Mitch, and this is going to be the first in a series of YouTube videos that I am making to explain various interesting topics in mathematics. Since this is the first video, I am going to briefly explain my background. I got my PhD in theoretical particle physics and cosmology from Rutgers University, and I now work as a signal processing engineer. In all of my career and my work, I have gotten to study math and learn about how math works at a deep level and see how math can be applied to reality in a very concrete and practical way. And I want to be able to convey some of these ideas that I have found so interesting in my work to you all. So I am planning to make these lectures both interesting from the mathematical perspective, but to have the ultimate goal of giving you the backing needed to understand topics in physics and computation, such as quantum mechanics, general relativity, machine learning, and more. Um, so the first topic that I'm going to cover in these videos is going to be vectors and vector spaces and linear algebra. I find that this particular topic is extremely useful for understanding the theories of physical reality and computation that I want to cover. Also, these topics are very rich and interesting from a mathematical perspective. So I thought this was the perfect set of topics to start off with. This particular video will be mostly about definitions of vector spaces and maybe a little dry or boring. If that's the case, do not fear. I plan to make the subsequent videos more interesting as we build up our mathematical machinery. I think that naturally will happen. However, I do want to cover things in the proper order and not jump ahead, which is why I am being careful in making those definitions here. So bear with me and enjoy. And I'm happy you're here overall. I hope that you gain a lot from these videos. If you have any questions about the material or just ideas of what you would like me to cover in future videos, please drop a message in the comments section and I will read it and address the comment either by answering in the comments section or answering in another video, or it may help me decide to make a whole nother video to address your comment in particular. So I really want to give the audience what they are interested in while still, obviously adhering to what I find interesting too and what I have knowledge about. So with that, here we go. Enjoy. I'm going to define what a vector space is and what vectors are to start off. A vector space is a collection of objects, which are called vectors, that satisfy a set of axioms. I'm not going to go through all of the axioms in detail, but basically there is closure under addition. That's one that I'm going to go over. And that just means that if I take two vectors, v and u, in the vector space capital V, there exists an addition operation, which is written with the plus sign, just as you would expect an addition operation to be, where these two vectors can be added together and we get a third vector, w, which is also in the space. So every possible pair of vectors in the space, when you add them together, you get another vector that is also in the vector space. And just as a notational detail, I will typically write vectors as lowercase letters with an arrow over top of them. And then the symbol for the vector space, which is the whole collection of all the possible vectors, is going to be a capital letter, which in this case I'm using V. All right, and then there's closure under an operation called scalar multiplication. So in this case, I'm specializing here to a real vector space. So I guess I'll write real vector space We will talk about other examples of vector spaces, but for now, that's what we are doing. So in that case, scalar multiplication can be done with a scalar, which is just a number. I'll call it C. In this case, it has to be a real number. And if I have a vector v in the vector space, then C times the vector v will also be in the vector space. Okay? And in addition, each of these operations, addition and scalar multiplication, have a set of other axioms, which I will show briefly right now. For addition, there's commutativity and associativity, which are kind of like what you would expect for any kind of addition to have. You probably learned these in grade school when you learned about addition. There's also an additive identity, which is just a vector that when added to any vector gives that vector back. There's an additive inverse, which says that each vector has its own inverse, which when added to the vector gives you the identity 0. And then for scalar multiplication, there's distributivity, which is again something you would expect a multiplication operation to have. Compatibility, again, another thing you would expect. And a scalar identity, which just says there is an element that when multiplied by a vector gives you back that vector for every possible vector. But I'm not going to prove each of those for each example that I talk about. I will just focus on what do the two operations, addition and multiplication, look like for each example. And so if these definitions all sound a little bit opaque and abstract, that's okay. That's what I would expect. And that's what these examples are going to help make a little more concrete. I'm going to start with a really simple example. So the real number line. So V is equal to the reals is going to be a vector space. So this is just all of the possible numbers. You have 0 somewhere in the middle, and positives to the right, and negatives to the left, all the way to positive and negative infinity. Now, this is going to sound really obvious because basically addition is just going to be what you learned addition to be for real numbers in grade school. So let's say I have a vector v is equal to 5 and a vector u is equal to 8. Then v plus u is just 5 plus 8, which is 13, which is also a vector in this vector space because it is indeed a real number. So this is addition, and multiplication is again just going to be exactly what you learned about in grade school. So if v again is 5, and let's make c 2. Now the real numbers is a special case because the set of vectors coincides with the set of scalars. In other words, the possible values that the scalar c can have are in the reals, but that was the vector space we were working with from the start. So this is a unique property of this particular vector space. And if I want to do c times v, it's just going to be 2 times 5, which is 10, which is also in the reals. And you can imagine that, I just showed one example for each of these. I'm not necessarily proving anything, but I'm just giving you an idea of how it works. And I think you can convince yourself that if you take any possible pair of vectors for the addition property and any possible vector and a scalar for the multiplication, you will always get an output of another real number. Now I'm going to give an example that is probably more of like what you think of when you think of vectors, if you had ever learned about them before, and that is arrows in 2D, such as maybe velocity in 2D that you may have learned about if you took a physics class at any point, or even if you took like a calculus class. This is a common example. And you'll see that there's additional structure in this. I'm going to write the vectors as arrows on a two-dimensional plane. And by doing that, I'm kind of implicitly assuming additional geometry that exists in this vector space that I haven't quite formalized yet. And I'm going to just go ahead and do that. And later on, I will point out what that additional geometry is and what gave me the license to be able to do that. But I think even without all of that, this should make decent sense. Like I said, a vector in this space can be thought of as an arrow, like that. It has a magnitude and a direction. So the direction is, what is the angle it is making with the, let's say, with the horizontal. It could point in any possible direction. I could rotate it anywhere around there, and it would still be a vector in this space. Also, I can stretch it and shrink it, and it would still be a vector in this space. So if I want to add two vectors, let's say they look like this, V and U, different lengths and different directions. The way to do that is just place them head to tail. So I'm just going to translate U to here so that they are in a good configuration so that I can see what the sum would look like. So I'm moving U like that. And then the result is just going to be from the tail of the first to the head of the second. So this is U plus V, which is the same as V plus U. Okay, so, and as you can see, no matter what direction U and V, I think you can convince yourself no matter what direction they're pointing in, if we do add them together like this, the result will also be an arrow in this two-dimensional plane that is the screen, and therefore will also be a vector in the vector space. So this is also in V. All right, and then multiplication. I'm going to take the same vector V and I'm going to multiply by a C equals 2. The way that looks in this vector space is I just take the vector V and I make a new vector in the same direction but twice as long. So this is 2V, where C is equal to 2. And clearly, no matter what that factor is, whether I make it twice as long, 3 times as long, any amount as long, it will still be in the set of arrows in the two-dimensional plane. If I had made that number C 1/2, then it would be half as long. This is 1/2 V. Again, still in the vector space V. So that gives you a taste of why arrows in 2 dimensions are also a vector space. Example 3. So this is going to get a little more abstract. This is multinomials, which are basically, if you've learned about polynomials, which are functions with powers up to x squared. Multinomials can have any power. So in this case, I'll say multinomials of degree n. If n was 2, that would be a polynomial. So a multinomial of degree n would look like the following. F of x, it's a function, is equal to a constant plus a constant times x plus all of the powers up to the final one, c sub n, a constant times x to the n. So this vector is really a function of all values of x. We're not thinking of it as being evaluated at any particular value of x. It's the whole function. So just to show you how vector addition works, let's say we have f of x is equal to this thing, which is going to be a sum from m equals 0 to n of c sub m x to the m, which is just another way of writing what I have above. And then let's say we have g of x is equal to the sum from m of 0 to n of d are going to be the constants, d sub m x to the m. Now if I add these, the way it works is we just match up the powers and we add the coefficients. So it's just going to end up being the same sum, but with coefficients that look like c sub m plus d sub m times each of the x powers. And clearly this is also a multinomial of degree n, so the sum is also in the vector space. And multiplication. Let's take the same f that I had above, which has the c sub m's, and let's do a constant a times f, and let's write what that is, where a is a real number, as it must be. So then each term in the sum would just get a factor of a, and we'll still have x to the m, and clearly that's just taking whatever the coefficient was, which was a real number, and multiplying by a real number, which gives another real number. So now I again have coefficients that are real numbers of a multinomial of degree n, which is also in this vector space. And if you want to see how that works out, if I was to write it all out, a times c0 plus c1 of x plus cn x to the n, so a times that whole thing, we can distribute the a, we get a c0 plus a c1 x plus a cn x to the n. So each of these are still appropriate coefficients for each power of x, and therefore this is in the vector space. And you can see that if I was to consolidate it again with the summation sign, I would just get what I have above right here. Okay. The last example is going to be a little bit different, and that is I am going to imagine the macronutrients of different plates of food, or different combinations of ingredients of food, as a vector space. And the macronutrients are fat, carbs, and protein. All right. So let's say I have chicken is going to be represented by one possible vector. I'll call it C. And I will write these vectors as the fat followed by the carbs followed by the protein. It's going to be grams of fat, carbs, and protein in 100 grams serving of the food. So fat for, this is chicken breast, is 3. Carbs is 0. Protein is 23. And then let's do quinoa. Which I'll call Q. Okay, and I'll write over here, this is grams per 100 grams of the food. Quinoa is 2, carbs 21, and protein is 4 grams per 100 grams. Okay, so how does addition work? Well, that would be like if I want to know what's the nutritional content of 100 grams of chicken and 100 grams of quinoa. And that would be C plus Q. And the way that that addition should work is it should be just the sum of each component. So I will do fat plus fat, which gives me 5. 0 plus 21 gives 21. And then 23 plus 4 gives 27. So this is the number of grams of fat, carbs, and protein in 100 grams of chicken and 100 grams of quinoa. Now, if I want to multiply, let's imagine if I want to multiply by a factor of 2, I'm going to write down 2 times C. And the question I'm answering is how much of each nutrient is in 200 grams of chicken, which is twice what I have quoted in the vectors above. So that would be 2 times C would give me the amount in 2 grams of chicken, 200 grams of chicken. So that would be just 2 times each component, as you would imagine. 2 times 3 is 6, 0, and 46. And again, the results of each of these additions and multiplications gives another combination of food. So any possible combination of food can be represented in this vector space.